Today's task, we're going to be looking at how alternators work. Now, an alternator is just a fancy name for a generator that generates an alternating current. So, if you imagine you have a magnetic field and you have a rectangular ring that's inside that field, it's going to experience a flux linkage. So, me spinning this in this field is basically the equivalent of having a coil in a magnetic field like we were talking in our previous videos with an angle of theta, and that would give us the flux linkage equation of which again we've spoken about in a previous video. So as this spins in that field, it's going to start generating a flux linkage, and because of that the output voltage is going to change direction when every half a term, because here it's at an absolute minimum. As it spins, it starts to increase until it's cutting the most field lines and is at a maximum. But then as it goes past that point, the voltage and the current are going to flow in the opposite direction, goes round, back to being at a minimum, etc, etc, and it continues like that. So we're going to be looking at how this can be plotted and how you'd use those plots. So if I was going to plot the flux linkage on a graph, so I'm considering this is my maximum BAM and this is my minimum BAM, because as I said it's going to alternate in different directions. This is going to show me what exactly your coil is doing in that field. So here's the equation we're going to be referring to. So at the start, when my coil is parallel to the field, we're going to have no flux linkage, so that's where we're going to start off at. Now, as this begins to turn all the way through to being perpendicular with the field, my flux linkage is going to increase. So as it's turning to be perpendicular, that's going to end up going up and 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 up till it hits a maximum. Now, once it goes past that perpendicular point, again it starts dropping back down until it goes back to being parallel again. As it spins back round to being perpendicular, it's going to go the other way, but in the opposite direction. And then back to being parallel, where we're going to come back up through to the top. So we start getting a graph that looks something like this. But if I was to consider the EMF in this circuit, my graph would be ever so slightly different. Now, if I'm considering that, it's going to obviously need to rely on this, because it's going to be the coil spinning and the flux linkage and how it's interfering in the field that's going to cause the EMF. So while I'm doing this, I'm just going to have this sat here so we can see exactly what my wave was doing before compared to after. So the flux linkage is pretty much the opposite of what the EMF is going to be. And now I'm going to explain this in a little bit more detail in a second, but I just want to show you graphically what I'm talking about. So when my flux linkage, is at a minimum, my EMF is going to be at a maximum. So when my wire is parallel, this is going to be at a max, that's going to be at a min. However, when it gets to being perpendicular, EMF is going to be a minimum and flux linkage is going to be a maximum. Again, back to being parallel, but in the opposite direction. Then we're going to go back to being perpendicular, so up to the centre, and then back to being parallel. So we're going to get this kind of shape instead of that kind of shape. Ooh, there we go, like that. Now, any genius will probably have cottoned on by now that it's going to be completely dependent on how fast that coil is spinning and obviously the angle in which it's going through. So the equation we know for flux linkage, due to it spinning in the field, is going to be adding on the cos theta. But from when you did about waves, you should know that theta equals your angular speed, omega, times by the time in which it takes. So another way of writing this equation out is Now this is handy because in the exam you sometimes get given things in radians per second, in which case you're going to be substituting that in for your angular speed here. Now the same thing applies to our EMF. However, with our EMF, where our EMF is the rate of change of flux, so a little bit like acceleration is the rate and change of velocity, we times it, well, we divide it again by the time, so it's meters per second per second. Here we're doing very much the same. So here's our speed in which it's spinning, our omega and our t, to find our angle in which it's gone through. But we're then going to times it again by our angular speed because it's the rate of change. So because of that, our EMF is BAN omega sine omega t. So that's where this equation comes from, and that's how you can understand where on earth that extra little omega has come from as well. So, an exam style question of doom. Now, I'll give you a second just to have a quick read, but a rectangular shaped coil with 30 turns of area of 0.2 meters squared is rotated in a field of 1.5 times 10 to the minus 3 Tesla, so 1.5 milliteslas. It is rotated at 20 radians per second. What is the maximum EMF? Now, we would go about this straight away. EMF, we know we're going to be using the following equation. You know you're going to be using that one because that's the one for EMF. So now all you've got to do is substitute in the values you know. Now, we know that if our omega t, our angle, is going to be at a maximum, if we're wanting maximum EMF, then our wire when it's spinning is going to be parallel, okay? So due to it being parallel, we're just going to times it by 1. Because that's what it would be in terms of the angle times by the sine. So it's going to be 1.5 times 0.2 times 30. Our omega t we're not going to worry about, and the omega that we've been given as our angular speed is 20. Okay, now we don't know whether it's going to be plus or minus, so you just need to make sure in your answer you put plus, minus, and whatever value you get. Otherwise, you can be deducted marks for not recognising that. So that would give us an answer. So if this makes it easier for you. Of 0.180, remember your standard form, volts. Now when I do that, always make sure you add your plus and the minus at the start to ensure you've demonstrated your understanding of it being a alternating current or voltage. So that's that. Next time we're going to be looking at alternating currents and using oscilloscopes. So see you then. Bye.